So the extreme value theorem. All right, so a function f has what we call an absolute maximum at C if f of C is greater than or equal to f of x for all x in the domain of f. Okay, so I'm going to write this, where D is the, okay, you all know what the domain is, right? Okay. Of f. Okay, and this is for all, we're going to use this symbol. I don't know if you've seen this symbol before. Okay, this is a symbol meaning for all, for every possible value x of D in the domain. Okay. Okay, so a function has an absolute maximum at a value c if what? If f, the value of the function as c, is bigger than or equal to every other value of f, for every other c. Whatever x you put into f, you will never exceed f of c. That means that f of c is the maximum value. Make sense? Okay, so let me just write this down. Fc is called the maximum value of f on D. Okay, so I'm going to make a little diagram after so you're going to understand. Let's do the same definition now for the absolute minimum. Okay, so a function f has an absolute minimum at C if, can you tell me, what can I write here? What should I write?
Smaller or equal?
Yeah, so if f of C is smaller than or equal to f of x, and for all x in the domain. Okay, so this is our symbol for all, because I'm very lazy. I don't want to write for all every time. I'm just going to use this symbol. Okay, it's very good for you to get used to math symbols. I'm going to save a lot of ink. Okay, and of course f of c is called, what's it called?
Absolute minimum.
It's called the minimum value. Okay, it's called the minimum value of f on the, always on the domain. Okay, now the maximum and minimum values of f are called we call them the extreme values. of f. Any questions until now? Just definitions, okay? So let me just draw a little, maybe a little picture so that you can understand what's going on. Although I'm sure you do, but so here we go. So let's say I have a function like this. Okay, on a certain domain. Okay, so on a certain, it's defined, the function is defined from A to B. So let's say this is A and this is B. Okay, so there's a certain value here. I'm going to call this value C1. Okay, where the function reaches a maximum value. And this point here is called the absolute maximum. Okay, and there's another value here, C2. And of course, this is the absolute minimum. Okay, now this value here of y, and this value here of y. Okay, so this is f of C2, and this is f of C1. Okay, so this is called the maximum value, and this is called the minimum value. Okay, makes sense? These are the definitions. So everything I wrote up here, I just expressed on a picture. I think picture is much better. Okay, let's go with two more definitions. Are we done here? We need more time to write. Tiffany, you still writing? You done? Yeah? Anybody else?
Can you wait a little bit, please?
Yeah, go ahead.
All right, thank you.
Okay, good. Let's keep going. Okay, so I'll change paper here. So two more definition and then the big theorem. Okay, so a function f has a, so the word here is a local maximum. Okay, so before we had an absolute maximum, now we have a local maximum. Okay, or we also call it, you've probably seen this in high school, a relative maximum. at C if, so again, f of C is greater than or equal to f of x, okay, when, okay, so before it was for all x's, every possible value of x in the domain, now not for every possible value, just when x is near C, okay, so I'm gonna write this when x is, so near, you don't know what near is, C. Okay, so what does near mean? For some open interval containing C. Okay, so this is a bit more difficult of a definition. I'm going to let you finish writing, and I'm going to explain what this means. Okay, let me write down the same definition for the local minimum, relative minimum, and then I'll show you what this means. Okay, this, especially this idea of near. This is weird a bit. Okay, so a function f has a local minimum, okay, so or relative minimum at C, same idea, if f of C is less than or equal to f of x when x is again near C. Okay, so here's a function. Okay, you guys I continue. Okay, so what's going on here? So right here is where I have a relative or a local maximum, and here is where I have a local minimum. Okay, so what's the difference between here and what we had before? Can you tell me?
The function is going towards infinity, so it does have an absolute maximum, but like we can't calculate it.
Okay, so in this case, it doesn't have an absolute maximum. There's no maximum.
Exactly.
Okay.
It's infinity.
Okay, so it goes on to infinity, exactly. But still, this is still a little maximum. Okay, so there's sort of a bump here. So what this means near here what we mean by near is that if this value is C, okay, so let's call this C, let's call this C1, okay? So if I take a open interval, okay, so I take an interval around C1, okay, well, every x in that interval has an f of x that is smaller than f of C1. Do you understand it? Okay, so if I could find an interval around C1, so an interval that contains C1, for which f of C1 is bigger than everything in there, then we call this a relative maximum. Okay, so this is a bit more complicated. Okay, when you start talking about what we call a neighborhood, okay, it's a neighborhood around C1. That's the real technical word, okay? It becomes a bit more complicated. This you do in university more and more intense, okay? But for now, okay, what you have to understand is that to be for a value to have, a function to have a local maximum at C1, okay, it needs to basically be a little, it's like if he's the king of his little region. That's it, okay? He's right here, around here he's the boss. But if you go a bit further out of your neighborhood, right, there's people that are higher than him. Yeah, that's what it means, okay? Same thing for the minimum, okay? He's, this is C2, okay? So around C2, there's a little neighborhood where f of C2 is the lowest value in that neighborhood. Okay, so he's the lowest here. But if he goes a bit further out of his neighborhood, he's going to see that there's people lower than him. And that's the idea. Okay, so he's the minimum locally, but he's not the total absolute minimum. And same here, he's the maximum locally, but not absolutely. Is that clear? That's the difference. Yes, question?
Wouldn't the intervals be like much bigger than that?
Wouldn't they be much bigger? Why you say that?
Because like, why do they stop at those parts?
Oh, you mean I could have done the interval maybe until even here?
Yeah.
Right, what you're saying? Yeah, but the question is, if I could just find an interval, any size, for which he is the biggest, then it's called a relative maximum.
Okay, so the interval really doesn't matter.
If I could find an interval. So for example, if I had a function like this, okay, let's have a function like this. Oh, you can see, sorry, I'm gonna move up. Okay, if I have a function like this, okay, which is like that. Okay, and I'm asking myself, is this a relative maximum or minimum? Is it? Of course not. Because no matter what interval you take, let's say you take an interval like this, okay, for sure, in that interval, you're going to have something that's bigger than you. You see it?
Yeah, okay, I understand now. Thank you.
So in this case, you cannot find, no matter how small interval you look for, you find it, you will never be the king of the hill. Okay? Well, here, there is an interval, small. You're right, I could have gone this big. You're right. From here to here, I could have done. But this is enough. I'm already the king there. I could be the king even more. You're right. But I don't need to go that far. Okay?
Okay, thank you.
Okay, good. Okay, so now let me write down the theorem. Okay, so I'm gonna write it here.
So excuse me, could you have two local maximums or two local minimums?
Yep, absolutely. You could have a lot of absolute of local maximum. You're right.
In the same interval, eh?
What do you mean in this interval?
let's say you took an interval which also involved the other x value, which is equal to a local maximum right now. So or f of 1, I think, fc1.
I don't understand. I don't understand. I'm sorry. If
Let's say the interval you took would be would also include the other x value, which is right now equal to the local maximum.
what I want to show here is that C1, at C1, there is a local maximum. That's what I need to show. Now, what are you saying now? Let me understand what you're saying.
I'm saying if, for example, you took it, can it be possible to take a certain interval in which you would have two local maximums? So right now, there is a certain y, for example, for the FC1, but there's also another y we could see that is exactly equal to the same thing just a bit later when x is bigger.
Yeah, there could be more than one local maximum in an interval. That's what you're asking?
Yeah, that's what I'm asking.
Yeah, of course. There could be 20 of them, of course.
Okay.
But the question, what I'm saying here is, how do I know that what we're talking about is an actual local maximum? How do you know that? Okay, how do you distinguish between, how do you say this is a local maximum? Well, it's very simple. How do I know that what's the requirements for this to be a local maximum? Well, it's just that I could find an interval where everything around C1 in that interval is below f of C1. I could find a little hilltop if you want. That's what it's mathematically what I'm saying. And translating in English, what I'm doing mathematically is that I could find a little hilltop, no matter how small the hilltop. Even if the hilltop is very small, I could have a function like this. Let me draw here. Okay, I could have a function like this. You see this? I don't know if we, I mean, I drew it maybe too small. You can't see it. Maybe it's blurry in your picture. Yeah, I think it's blurry, but let's say I'm gonna not exaggerate it that much, but I could have something like this. You see this? Okay, so is this, I'm asking, is this a local maximum? Yeah, local maximum is this? Is it? Yes. You know why? Because I could, if I zoom in, I could find a certain interval here where he's going to be the top of that little region. He'll be the top. He'll be the king of his little neighborhood. I could find a neighborhood around him where he's the king. Make sense?
So, sir, I have a question.
Yeah.
The one on top, does it only have one local maximum and one local minimum?
In this picture?
Yeah.
Yeah, just one.
Okay,
And there's no absolute max, no absolute min in this one.
Okay, thank you.
Okay. Ask your questions. Okay, I'm not going to advance if it's not 100% clear. Okay, because these are the definitions and we're going to build on this.
Just to be sure, an absolute maximum and minimum, it's only when it's like when the function like stops, because this one goes just all the way to infinity. Is that it?
No, you could have a function that goes to, well, what do you mean stop? It stops vertically or it stops horizontally? What's your question?
Like I guess it stops for like it stops for like horizontally, like it doesn't keep going. I'm not sure.
No, because I could have a function like this. I could have a function like this. Look, okay, I'm going to erase this, but I could have a function like this. Let's say I have an asymptote here, goes up here, goes on here, and then I have an asymptote here. Here, I have an absolute max, absolute min, and it still goes on forever.
So what's the reason why that's an absolute and not a local?
Well, every absolute maximum is of course a local, because if he's the king of the whole function, then he's for sure the king of his little neighborhood. Okay,
Okay.
that's the idea.
So in the one that you drew with the local maximum, it's also an absolute maximum.
No, in this one here, up here.
Oh, because there's a one
No.
that's higher. Okay, yeah, never mind.
There's higher.
Okay.
But here there's no higher. Okay, it's clear?
Yeah.
Any other questions?
So then for the one that you drew right on top, the point that's higher than the local maximum,
There's a lot of them. Yeah. What do you mean? Why the point? The points, all of them. Yeah. There's a lot of them.
Okay, so they're still local maximums. They're not absolute maximums, even though they're higher. They're just like the local maximums of their intervals.
Who? Which one? A point here?
Like, yeah, if you take a point higher than the local maximum,
Yeah.
that's not the absolute maximum of the function.
It's not a maximum at all,
Why?
because let's say this point here,
Mhm.
it's definitely not a maximum because,
It's okay. Because
yeah, you understand? Should I continue?
no, because it's linear. It's not a, you didn't find a hill thing.
There's no hill, exactly.
Yeah.
There's no, okay. His immediate neighbor is higher than him, if you want. Okay, if you could say immediate neighbor, we can't say immediate neighbor in dense sets like this. Okay, there's no immediate neighbor to that point. Okay, but okay, this is more complicated questions.
Sir.
Yep.
So I'm not sure if I'm going to ask it. You can't have an absolute value and a local minimum maximum in the same graph, right?
1 second. An absolute value, you say? An absolute
Like
what?
the absolute. I forgot the rest of the word.
Maximum?
Yeah, that thing. Yeah, you can't have that in the same graph.
No, wait. Don't say that thing. The words are very important. An absolute what?
Oh. Huh?
What thing?
The absolute. Sorry, sir, I forgot the rest of the.
Yeah, well, okay. Go look at the paper. I just wrote it.
The absolute minimum. Yeah, in the
I give you 4 definitions. Just 4 definitions I give you. So memorize them right now and tell me. And use the right word.
Okay.
What's it? Okay.
I'm just gonna. Okay.
Go ahead.
So, for example, yeah. So, can you have an absolute maximum and a local maximum in the same graph?
Of course.
Yeah. Okay.
You know why?
No, I'm not sure.
Let me look at this picture here. Okay, let's go to the bottom one right here. So let's say I had a situation like this. Okay. Absolute max, relative max. Okay, absolute max, local max. Absolute minimum, local minimum.
Okay.
You see?
Yeah.
Okay.
Thank you.
He's the lowest. He looks around. It's very simple. This guy here looks around him and he say, "Hey, I'm the lowest in the world." And then there's another guy here. He says, "No, bro, I'm lower than you." You understand?
Mm-hmm.
Same here. This guy says, I'm the king of the hill of the world." He says, "Take it easy. I'm bigger than you." Okay? He's the absolute max. He's just locally. He tells him, "You're just maximum, but locally." Okay? You're very powerful in your neighborhood, but I'm the king of the world here. Do you understand the difference?
Yeah. Thank you.
Okay. Any other questions? Okay, good. So let me erase this thing here and let me write down the extreme value theorem. So this is important now. Okay, so every time you're going to see theorem, it's serious stuff. Okay, so the extreme value theorem. So if f is continuous on a closed interval, AB, then f attains an absolute maximum value. Let's call this FC, and an absolute minimum value let's call it FD, at some numbers C and D in AB.
Sir?
Yep.
What if it's an opened interval?
What if what's an open interval here?
Yeah.
AB?
Yeah.
Okay, it's a good question. Okay, we're going to talk about this. Very good question. Okay, and what if it's not continuous? Okay, there's a lot of little requirements in this that are necessary, and we're going to see what. Okay, it's a good question.
Okay.
Okay, so let's just understand the theorem now. That's the idea. Because based on this theorem, you will see that we're going to do some optimization problems and a lot of things. So it's very important to understand what does this mean. Okay, are you done writing? Anybody needs time? Okay. So what does this mean? Let me just go back here. Okay. What this means, it tells me that if a function is continuous, so we all know what continuous means. Okay. Continuous means I could draw it without lifting the pen. Okay. From A to B. Okay. So on a closed interval from A, so it starts at A, finishes at B, f of A, f of B, I draw a curve, any curve. If it's continuous, then for sure, it tells you that it's going to reach a maximum value and it's going to reach a minimum value. That's what it says. Okay. So let me just maybe draw an illustration of the theorem. Let's say, I went a bit far. Okay, so here's my function from A to B. Okay, so it's continuous. It for sure reaches a maximum value, which where is the maximum value here? Where? Here?
Yeah.
Here?
No, it's on B.
It's on B, right? In this case, here's the maximum value. And the minimum value is here. Okay, so there is a value here which we call C, where the function is at a minimum, and there is a value which we call D. In this case, it's B, where it is at a maximum. Guaranteed. There's no way around it. You're for sure going to reach a max or a min. That's what the extreme value theorem tells you, that you're going to reach the extremes. As long as the function is continuous and as long as you're on a closed interval. Okay, so the first question, why is the continuity requirement necessary?
Sorry, sir. What is that under the B?
Excuse me?
What did you write under the B?
Under the B, oh, I wrote D. Because I said D, the theorem, I said there's a value D where the function is, actually, no, I think it's the opposite. Oh, f of C, so no, that was, sorry, this would be C. Yeah, in the theorem I wrote C is where the maximum is, and D is where the minimum is. Okay, it doesn't matter, but C, and this would be D where the minimum is. Okay, so my question is, why in the theorem do we need to specify that the function needs to be continuous? Okay, apparently, if the function is not continuous, then we cannot say that the function will reach a maximum or a minimum. Okay, so let's do an example. Okay, so let's say interval A, B. Okay, let's say I have in the middle, there's an asymptote. For example, here's an example here, where it goes like this, and then it goes like this. Okay, and there's the function as a value, let's say. Okay, so the function, as you see, is defined on interval AB closed, including A, including B. But you see, there's no maximum, there's no minimum. Okay, it doesn't reach the maximum, it doesn't reach the minimum, of course, because it's not continuous. There's a problem in the middle. Make sense? You understand clearly? Another example here. Again, A, B, and here's another function. Okay, this time I will not do an asymptote. Open dot, and it goes here. And dot here. Get it? Do you see that it doesn't reach its maximum value? is this a maximum value? Not really, because it doesn't reach it. It doesn't attain it. Okay, so let's say this limit from the left, let's say it was 2, for example, then you'll get close, you'll get to 1.999999, but you'll never reach 2. So you'll never attain the maximum. Okay, same thing for the minimum, you will never attain it. Is that okay? Okay, that's why it's very important that the function needs to be continuous. If it's not continuous, then I could find functions where even though it's defined on AB, but it won't attain the max, or it won't attain the min. It could, but it doesn't guarantee that it will. Okay, the theorem guarantees that it will. Is that okay? Questions?
Sir,
Yeah.
if it's just like a removable discontinuity, then it could have one, no?
You could always have one. Even if you have a jump discontinuity, you could have one.
Okay, it just doesn't guarantee it.
It doesn't guarantee exactly. The extreme value theorem guarantees that if the function is continuous over a closed interval, guarantee that you reach the max and the min.
Okay.
Okay, I'll give you an example with a removable if you want. Okay, so I don't know, again, let's do A and B, and let's do a function like this. Goes up, empty, goes down here, and say a point here, who cares? Okay, as you see, there's a removable discontinuity, it doesn't reach the maximum. Okay, here's an example.
But there's a minimum, right?
In this case, there is a minimum, yes. Yeah, but if I wanted to put another removable discontinuity here, then there would be no minimum as well. Okay.
Okay, so what if that dot, it was like below like the minimum?
That dot, which one? This one here?
Yeah, that one. Yeah.
Then that would be the minimum.
Okay, so that could be the minimum too.
Of course. And if that dot was on top here, then there would be a maximum and a minimum in this case. Yeah, good.
Okay.
Okay. I'm just talking about guarantees here. Okay. So the other requirement, which is, I don't know who asked this question, was a good question. So why is the closed interval, so AB, necessary? Okay, so again, okay, so I could have a function like this. Okay, there you go. So the function is defined on A open B, A open, B open. Okay. And so you see there's no minimum, there's no maximum, it doesn't reach it.
So if your maximum or minimum is an open dot, that means you don't have a maximum or minimum, right?
Exactly. There's no maximum, no minimum, exactly. Okay, there's something else, okay, which is a bit more complicated. This you'll do in more advanced courses. And these are called upper bounds and least upper bounds and greatest lower bounds and lower bounds. Okay. Okay. There is a least upper bounds here, or the supremum, but it's not here. Okay. It's not in this course. This is analysis courses. Okay. Yes.
If it was closed on A or B, could we say like there's a minimum but not a maximum?
If it's closed on A,
But open on B.
in this example here, yeah, there would be a minimum but no maximum. Yeah, exactly.
Okay, thank you.
Exactly. Okay, any questions? All right, let's go. Let's go to Fermat's theorem. Okay, and that's what we're going to use a lot. Okay, so if f has a local minimum, a maximum or minimum, at C, and if f prime of C exists, then f prime of C equals 0. Okay, it's very important, this one. So let me do a picture to explain what this means. Okay, so if there is a maximum at C or a minimum, I just took a maximum in this case, it means that and if the derivative exists here, then the slope of the derivative, basically f prime of C, will be 0. It'll be flat. Which makes sense in a picture. Okay. And that's very, very important because that's what we're going to use when I'm going to ask you to maximize or minimize the function. Okay, because I want to know what's the maximum value of a function or the minimum value of a function. Well, I'm going to look for places where the slope is 0. Because these are places, right? Here, here, all these are places where the function reaches a maximum. Okay, and later on, you will see there's going to be places like this where the slope is 0, but it's not necessarily a maximum. Okay, but what I'm saying, what Fermat is saying is that if there is a max or a min and the derivative exists, the derivative is 0. Any questions?
But sir,
Yeah.
how do we know that there's like no flat spot?
No what? I'm sorry.
No flat spot in the function, because
you mean a spot like this?
yeah, like that.
There could be. What's wrong with that?
Then that's not a minimum or a maximum.
They're both. It's both. Every point here is a max and a min, local.
Oh.
Right? By the definition of being a local max or min, is that if you take any interval around this point, well, he's bigger or equal than everything else. In this case, it's equal, big deal. Okay.
Okay.
Is it clear?
Yeah, thank you.
Good. It's good. You're asking very good questions. Okay, these are questions very, very relevant, and you have to dig in like you're doing. It's very good. Okay, that shows me that you're understanding this. Okay, so are you all understanding this? You have to ask the questions like he just did. Okay. So I'm debating whether I prove the theorem or not. Well, we proved everything so far, so might as well. Okay. You don't want to prove it? Well, we didn't prove the extreme value theorem. Okay. This one we didn't prove actually, because this one requires some more advanced stuff. Okay. But this one technically we could prove, but I'm thinking about it. Yeah, it's not that difficult, but I don't think we're gonna gain much from this. Let's move on a bit, okay? Let's move on a bit, and if you want, I'll prove it to you, okay? But I want to reply this already, okay? Let me give you an example. Let f of x equals 2x cubed. Okay, so the question is, does f have a local, let's call this a local max or min? Okay, so I could be tempted to, well, I see that every place where there's a max or a min, the derivative is 0. So I'm going to ask for the derivative to be 0. I'm going to find it. Okay, so let's see. F prime of x is 3x2. And when is this is 0? F prime of x is 0 if 3x2 equals 0, which means that x has to be 0. And so I found one spot where the slope in all the function, all the domain, all of R, there's only one place where the slope is 0, and is when x is 0. Okay, so let me draw the graph. Do you know what the graph of x3 looks like?
Three curves.
Sorry?
It has three curves.
Three curves?
Two.
Two curves. It looks like this. That's what it looks like. Okay, so you see that at 0, indeed, the tangent is 0. Up a bit. Okay, so f prime of 0, yes, it's 0. But as you see, there's no maximum and no minimum there. It's not a hill or it's not a valley. Okay, so there's a lesson to be drawn from here. Okay, even though f prime of C is 0, that doesn't confirm that f has a maximum or minimum at C.
So how do we know? So we need to know the graph in order to know if it exists or not.
We're going to talk about this in a minute. Okay.
We didn't know the graph of x3. How would we know that there's
Yeah.
no maximum?
You're right. You won't. I'm going to show you how. I'm going to show you how very soon. Okay. We're going to do curve sketching, and you're going to know exactly how the graph looks like, and you're going to understand why there's no maximum here. Okay, or minimum. One quick thing is you look at f prime and you see that f prime is 3x2. Okay, that's the derivative. And as you see, x2 is always positive. It means 3x2 is always positive, which means that the slope is always positive, which means that the function is always increasing. So since the function is always increasing, it's for sure it can't be a maximum here since it's increasing always. Do you understand that?
Yeah.
Okay, that's one way to look at it.
Wait, sorry, can you repeat that, please?
Yeah, it's not that important. It's important, but not for now because we're going to go deep into this. But just if you wanted to think a bit, why don't have a maximum or a minimum at x equals 0 here? Well, you could just look at the derivative, and you notice that it's always positive. x2 is always positive. Okay, so if f prime is positive, means that the function is always increasing, right? A positive slope is increasing. And a function that's always increasing cannot have a maximum. Because for you to have a maximum, you need to start decreasing at some point. Even for a little second, you need to decrease a bit. Okay? So that's not the case. It just increases, stabilizes 2 seconds at 0, not even a second, and then goes back up again. Okay? And that's why there's no maximum here.
Sir,
Yep.
but you said that if there's a flat spot, then there is a local min and max.
Oh, if it's not a flat spot, I need to have I need to be flat on an interval.
Yeah, but how would you know, like, if you have a flat spot or not?
Okay, we'll get to that. We'll get to that. Okay. We'll get to that in detail. From this example, what I want you to pull from this example is that the fact that f prime is 0 does not guarantee that you have a max or min. But if you have a max or a min and the function is differentiable, the derivative exists, then for sure it's 0. Okay? You cannot have a maximum or a minimum with a derivative that's not 0. Can I continue? Am I going too fast? Anyone? Okay, it's a bit more abstract than what we've been doing so far, right? Until now, we're doing just technically calculating derivatives, limits, continuity, limits, derivatives. Now we have to think a bit, okay? And it's really understanding what the derivative means. Okay, let's continue. Okay, we have more time. So let me explain to you what a critical point is. So a critical point of a function f is a number, is a point where either f prime of, so a point C, where either f prime of C equals 0 or f prime of C does not exist. Okay, so it's a point really C f of C, C f of C. Okay, let me just, I went to the point, I don't want to do the point, just forget this, I'm going to rewrite the definition, okay? I don't want this, 2 seconds, okay? I'm going to show you first a critical number, okay? A critical number, before critical point, I think it's better. A critical number, that's better, of a function. F is a number, that's better. C, okay, in the domain of F, such that, so either f prime of C equals 0 or f prime of C does not exist. Okay, this is what a critical number is. Okay, that's better. Okay, so let me give you an example. Find the critical numbers of, so the function f of x is equal to, let's say, x to the power of 1/3 times 3 minus x. Okay, so basically what we want here is to find the derivative and see when is the derivative 0 or when is the derivative not existing. Okay, so let's go. We find f prime of x. Okay, so what is it? F prime of x. You know what that is? How do we do the derivative of this?
Quotient rule, product rule.
Product rule. So 1/3 x to the negative 2/3 times 3 minus x plus x to the 1/3 times -1. Good? Okay, so I'm going to pull out, I'm going to do a bit of algebra here, and I'm going to, or actually I'm just going to find the common denominator. So I will have 3 minus x over 3 times x to the 2/3 plus minus x to the 1/3. Right, that's what I have. And I will multiply here top and bottom to get the common denominator by 3x to the 2/3 top and bottom. Okay, so I have 3 minus x minus, well, x to the 1/3 times x to the 2/3 is x to the 1. So it's minus 3x over, and on the bottom I have 3x to the 2/3. And so I have 3 minus 4x over 3x to the 2/3. This is what f prime of x is. Questions?
Sir, can you explain the common denominator, please, again?
Sure. So what I did here is, so this is over 1. So I need to make this into the same as this guy. So that's why I'm multiplying by the denominator, 3x to 2/3, top and bottom. Is that okay? Hello?
Yeah.
Okay, so, and now I put everything on the same denominator. And this, if you multiply, x to the 1/3 times x to the 2/3 is x to the 3/3, which is just x to the 1 times 3. And then I just simplify the top and that's it.
Thank you.
Okay, so now when is it 0? So f prime of x is equal to 0 if the numerator is 0. So 3 minus 4x equals 0, which means that x will be equal to 3/4. That's a critical number because x equals 3/4 makes the derivative 0. Okay, so very important. You're gonna have to do this a lot, finding the critical numbers a lot. Okay, so very simple. You put f prime equals to 0 and you solve. If you have a fraction, you make the numerator 0. Okay. Also, if the denominator is 0, the derivative doesn't exist. Okay, so f prime of x does not exist if the denominator 3x to the 2/3 is equal to 0, basically if x is 0. So these are my two critical numbers. One makes the derivative 0, one makes the derivative not existing. All right. So let's go now. Let me give you an example. Well, I'm going to give you just one definition, one last thing, one thing to note. Any questions on this? You're still writing. Okay, 2 seconds. Go ahead.
Sir, how did you get the 3 minus x over 3x 2/3?
3 minus x, sorry?
On top, it says 3 minus x over 3x 2/3.
This?
Yeah, that.
I just sent the x to the minus 2/3. Since it's a negative exponent, I sent it on the bottom.
Oh, okay.
Okay.
Sure.
Yes?
Why does f prime of x, I mean, no, I know why it does not exist, but why is x equal 0, like after the arrow?
This here?
Yeah.
How would you solve this? Let me solve. Okay, so from here to here. So I divide both sides by 3. So x to the 2/3 is equal to 0/3. Is that okay?
Yep.
And then I'm going to put both sides power 3. I'm going to get x2 equals 0. And then I'm going to do square root of each side. I'm going to get x equals 0.
Oh, but we do it even if it does not exist?
Of course, I'm looking for the value of x that would make the denominator here be 0, and therefore the derivative not exist.
All right.
Okay? Any questions before I continue? Okay, let me give you one little note here. Okay, so note, very important one. If f has a local maximum or minimum at C, then C is a critical number of F. Okay, that's going to be very useful to us.
Then what is the difference between a critical number and a local maximum and minimum?
The difference between a, okay, so the critical number and the local maximum and minimum?
Yeah.
The critical number is this. Yeah.
But doesn't that also correspond to local maximum?
What do you mean? No. If you have a maximum here, a local max, then this is for sure going to be a critical number. That's what I'm saying. It means that at this point, two possibilities. Either the derivative will be 0, or the derivative won't exist. That's what I'm saying. That's what the mathematician said.
Okay, thank you.
Okay, do you understand the difference or not?
Since you said like the derivative is equal to 0 doesn't always mean a local maximum, then yeah, it makes sense. Local maximum.
No, 1 second. If I'm not sure I heard what you said correctly, but if the derivative at that point is 0, that doesn't mean that I have a maximum or a minimum. But if I have a maximum, then for sure the derivative here is either 0 or doesn't exist. Okay, that's what I'm saying.
Okay.
Okay. Anyways, let's do an example here, an actual example with numbers now. And you will see that all this enough with the theory for a bit. And let's understand.
Sure.
Yeah.
Sorry, can you go back to the note? I wasn't able to finish writing.
No, sure. On the bottom.
Yeah.
Go ahead. Let me know when you're done.
I'm done. Thank you.
Done? Okay. Okay, let's move on. Okay, so example. Find the absolute maximum and absolute minimum values of the function. Okay, so I'm going to take this as an example from the book. F of x equals to x3 minus 3x2 plus 1 on the interval, so on the closed interval, minus a half and 4. Okay, so basically, I want to see this function. So I see that it's continuous. Okay, you see that it's a continuous function. It's a polynomial. There's no restriction. There's no square root. There's no log. There's no denominator. There's no problem here. Okay, a polynomial is always continuous. And it's on a closed interval from minus a half included until 4 included. So according to the extreme value theorem, guaranteed that this function attains its maximum and attains its minimum, right? It attains its extreme values. Are you clear with this? Okay. So what are we trying to do now is we're trying to find the maximum and the minimum.
Can you repeat that, please?
Yeah. I'm going to write it actually. Okay, I'm going to write it. So since f of x is continuous. Okay, so just to notice, a polynomial, you know what a polynomial is? Function is always continuous. Okay, so since it is continuous over a closed interval, okay, so it's a closed interval, then so I'm going to write the EVT, okay, so the extreme value theorem. I'm going to just write it for now once so that you know what it is in your notes. So the extreme value theorem. F attains a maximum and a minimum value. Make sense? Okay, so it's better when I read it.
But sir, there could be both, right?
Both what?
Absolute like maximum and relative maximum.
Yeah. There could be maximums and minimum relatives, of course, no problem.
But how do I know if it's absolute or relative?
Okay, so we're going to talk about it now. Okay, we're going to talk about it right now. Okay, so the question here asks you to find the maximum and the minimum values. So I know what I just wrote here is that if it has a maximum or a minimum, local or maximum or absolute, who cares? If it's local, it's for sure maximum. If it's maximum, it's for sure, I'm sorry, if it's absolute, it's for sure local as well, okay? But if it reaches, if it has a maximum or a minimum, at that value, the function has a critical number there. That means that it's a place where the slope is 0, the derivative is 0, or doesn't exist. Okay, so that means that here, what I have to do is I'm just going to find that when is the derivative 0. Okay, so where is the derivative 0? And that's going to tell me where potentially I have a maximum or a minimum. So let's find the derivative. 3x2 minus 6x. When is that equal to 0? So I'm going to pull out a 3x times x minus 2 equals 0. X equals to 0 or x equals to 2. These are the two places where I could find a maximum or a minimum, local. And maybe absolute, I don't know, but at least local for sure. Okay? So what I'm going to do now is I'm going to find the value of the function. So let me go back here. I'm going to find the value of the function at these points, at x equals 0, at x equals 2, and at the end points. And I'm going to see what it gives me. So let's find f of negative 1/2 equals what? Then f of 0 equals what? Then f of 2 equals what? And then f of the endpoint 4 equals what? Let's find all these. Okay, by plugging into the function. Okay, so let's plug in negative 1/2 into here. So if you do that, you will get 1/8. If you plug in 0, you will get 1. If you plug in 2, you will get 8 plus 1 is 9. 9 minus 12. 9 minus 12 is negative 3. And if you plug in 4, you'll get 64 minus 48 plus 1, you get 17. Minus 1/2, 0, 2, 4. So minus 1/2, it's 1/8. At 0, it's 1. At 2 is minus 3. And at 4 is 17. Okay, so my function looks like this. So what is the maximum value?
$17.
17. Very good. So this is the maximum. And the minimum, of course, is minus 3. Okay, there you go. You can see it on the graph. Min, max, and that's it. We're done. You see how it works? Okay, so I found, how did I find the 0 and the 2? Okay, these are two values in my interval where the slope is 0. Okay, so these were potentials for being the absolute max. This one ended up being a local max, and this one ended up being the absolute min. Okay, local max because there's one higher than him. Because when I check the endpoints, I checked 4 is higher. When I check minus half, it's here. It's not the lowest, it's not the highest. That's okay. That's nothing. Are you with me? Okay, and that's how you find the maximum or the minimum value of a function over an interval.
But these are local, right? Because
Which ones? Which ones?
Well, -3 and 17.
Okay, so the
-3 and 17. They're well, no, they're absolute. They're in this case they're absolute. This is absolute. They're local.
Yeah, but
also. They're local also.
It's over. Exactly.
But they're the absolute minimum and the absolute maximum. Yeah. There's nobody lower than him, nobody higher than him in the interval.
Okay.
Sure.
Yeah.
But that means we didn't technically have to draw the graph, right? We could have just
No,
picked
you
out
didn't
the lowest and the highest number.
Exactly. You could have just done this.
Okay, thank you.
Okay. But I do it for you here because it's very important to visualize what's going on. Okay. Why did I check the endpoints here? That's why. Okay. Because if I didn't check the endpoints, I would have found 1 and -3. I'd say, oh, that's it. Here's the maximum. Here's the minimum. You understand? Because I won't spot number 4 because at 4 the slope is not 0. It keeps going. If I allow it to go further, it would keep going higher. Okay? It's just the fact that I'm stopping it at 4 that makes it a maximum. Is that clear?
Yep.
I guess so. Okay.
Sorry?
Yep.
The absolute minimum, absolute maximum of this case, it is the absolute maximum and minimum only of our interval and not the whole function. Am I right?
Of course. Yeah. Exactly. Exactly. Any other questions? You want to try one, maybe? Okay, try one. Find the absolute find the extremes. Okay, so instead of absolute maximum, absolute min of f of f of x equals 2. So let me see an interesting one here. X4 minus 2x2 plus 3 on the interval closed -2, 3. So again, f prime of x equals to 0 means that, so the derivative is 4x cubed minus 4x equals 0. Pull out 4x, x2 minus 1 equals 0, 4x, x minus 1, x plus 1 equals 0, which means x equals 0, or x equals -1, or x equals 1. Clear? That's what you did, right? And then I'm going to check the value of the function at the endpoints and at all these ones, as long as they're within my interval. So let's go. F of -2, f of -1, f of 0, f of 1, and f of 3. Okay, let's go. F of -2 is 16. 16 minus 8 is 8, plus 3 is 11. Okay, then minus 1, I get 1 minus 2, so 1, 4, 2. F of 0 is 3. F of 1 is 2. And F of 3 is 81. So 81 minus 18 plus 3. So I get 66. Okay, so the maximum value is right here. And the minimum value will be 2. It reaches the minimum at 2 places. At minus 1 and at 1, it reaches a minimum value. Is that clear?